Dear students, welcome to Atoms to Infinity. We are going to do a worksheet today, and that worksheet is upon sound, and the difficulty level is at IGCSEs, GCSEs, or O levels. So we are going to start this. And one thing more, I would be explaining each and every MCQs to you, so that if you have still any question, you can actually reach me out through the comments. Right, let's start. So this is going to be on sounds. Mind my writing, because right now I don't have a graphic tablet, but in a couple of days I'll be arranging it for lectures, etc. Right, why can ultrasound not be heard by humans? Well, the audible frequency range for humans is from 20 Hz to 20 kilohertz, where kilo is basically 1000, a prefix. So what option can be correct? The amplitude is too great? No. The frequency is too great? Yes. That is correct, because the typical frequency of ultrasounds is basically greater than 20 kilohertz. Right, question number 2. A sound wave has a certain amplitude and a certain frequency. A second sound wave is quieter. Now when we say the word quieter, that would mean low amplitude. And lower in pitch, that would mean low frequency. So if I try to recreate this scenario here, so this is our wave number 1 with higher amplitude. You can see the amplitude is very high and frequency is very high too. But for the second wave, we have lower amplitude and lower frequency. So this is wave A, this is wave B. Both are, let's say, sound waves. Okay, so the first one has a higher amplitude and frequency. The second one is the exact opposite. All right, so the second wave would have a low amplitude and low frequency. So option D is correct, a smaller amplitude and a smaller frequency. I hope you understood this concept. By the way, this was a transverse wave. We do know that sound waves are longitudinal, but just in order to recreate this scenario here, I had to recreate it here. Right, let's go to question number 3. What is the approximate range of hearing of a healthy human ear? By the way, I told you that already. So it is going to be 20 Hz to 20 kilohertz. Option D is correct. Right, a singer sings 2 notes. Notes are regular vibrations. I'm just going to write REG for regular and V for vibration. These are musics and melodious sounds, whereas all the other irregular voices or sounds, they are just noise. So the first note is louder. So the word loud means it has, not low, but high amplitude, and lower in pitch, that would mean low frequency. Then the second note, so that would mean a second note would have a low amplitude and higher frequency or higher pitch. Let's see. Now we have to compare these two. The first note has a larger amplitude, that is correct. Larger frequency, that is incorrect. The first note has a larger amplitude, correct. Smaller frequency than the second note, that is correct. So option B here is going to be the correct one. Alright, now let's go to the question number 5. Which range of wave frequencies include only sounds that can be heard by human normal hearing? Okay, now that we do know 3 Hz not possible, 30 Hz to 3000 Hz, that is possible. 300 to 30,000 of course not possible, and 300,000 certainly not. So option B is correct. Okay, now in question number 6, we have a loudspeaker. The loudspeaker is going to produce sound waves, and here we have a candle flame, and we want to basically observe in which direction the candle flame would vibrate or move. Now since the loudspeaker will produce sound waves, so in sound waves, molecules or particles move back and forth, or you can say horizontal to the direction of propagation. If this bigger arrow was a wave which was propagating, or it was a progressive wave, a progressive longitudinal wave, here I'm drawing a longitudinal wave. You can see some areas where air particles are closer and some areas where air particles are far away. These are rarefactions and these are compressions. So the candle flame should also vibrate back and forth. And of course sound waves are longitudinal, and like I told you, don't mind my writing. So in these four options, C is to be the correct one. In C, we see this particular direction of vibration and it's longitudinal, so it is correct. Okay, let's go to the question number 7. A sound wave travels from a point X to another point Y. So we have a sound wave, by the way. So we do know that particles between X and Y, all the particles between X and Y will vibrate back and forth. So here we have a back and forth direction in option D. So option D is the correct one. Alright, question number 8. Sound wave P has a greater amplitude, means it's loud, and larger wavelength. That would mean low frequency, because wavelength and frequencies are inversely proportional. So if a wave has a larger wavelength, the frequency would be lower in air than sound wave Q. So how do loudness and pitch of the P compare to okay, we have to compare P and Q, and both are sound waves. So Q is going to be the exact opposite of P. So Q is going to be quieter. Quiet sound means low amplitude, and it's going to be higher pitch. It will have a higher pitch, H-I-G-H, higher pitch or frequency. Right, P is louder and higher in pitch. That is incorrect. P is louder and lower in pitch. That is correct. Now this option B is correct, of course. You can still search the other two. P is quieter, of course it's not quieter, and P is quieter, certainly not. So here we have only option B left, which was correct. Now in question number 9, we have a ship, and that ship is sending a sound wave to the seabed. We can see this by arrow, which is like incoming arrow to the sound to the seabed. So sound is covering a distance d from this point emitter to this point, and then it is reflected and received. So when it is getting reflected or getting received at the ship, it covers the same distance. So collectively it is covering twice the distance. We do know the formula to find the speed of the wave, that is v equals to d over t, distance over time. But here we would have to include a factor of 2, this one, because the sound wave is covering twice the distance. Now each and everything is given: 2 seconds, 1500 meters per second, that is velocity, that is time. So we just need to rearrange this formula to find the depth of the sea. Let's plug in the values. 1500 into 2 divided by 2 equals to d. So 2 and 2 will be cancelled. So 1500 meters, that is a seabed. That is the depth of the sea. Well, not much of a depth. It's around about 1.5 kilometers, but still, we had to find the depth. We found it. Right, which frequency produces a sound that can be heard by a person? 30 kilohertz, we cannot hear it. 20 hertz, no. 2 hertz, no. So 2 kilohertz can be heard. So yeah, it corresponds to this frequency range. So of course we can hear it. Right, question number 11. Here we have a glass block in which there is a ray of light which is making an angle x. That angle is called angle of incidence, and that wave is getting out of the box. It's going into the air. So it is like getting refracted. Remember the phenomena in which a wave traveling in a particular direction, when crosses the boundary of a medium, this is the boundary, which is dotted line, so it changes its path instead of going in the same direction. This phenomena is called refraction. Now this is angle of refraction. Now it says that which row's table describes the change of the value of angle x, the name of the effect produced. Alright, so if we increase the x, or the angle of incidence, then angle of refraction would increase again. So don't worry about this MCQs, because then I'll be explaining the chapters related to light, electromagnetic spectrum. So we will be studying in depth that how angle of incidence and angle of refraction are related. So just for the reference, if angle of incidence is greater than 90 degrees, then this wave will never be able to leave this block, and that will be internally reflected. This phenomena is called total internal reflection, not refraction. So option C is correct one, because we would have to increase the angle of incidence, and after increasing it more than 90 degrees, the wave will be totally internally reflected. That option C is correct. Now, which row states two properties of sound waves? Well, we are talking about the traveling, so sound waves need a medium to travel. Means they need the help of the atoms and molecules or particles in general. So there are a lot of sounds in the space, a lot of explosions, but we are not able to hear them because there is no medium between Earth and those stars, distant stars or galaxies, etc. So, and then we also know the specific nature, which is the sound wave is longitudinal wave. Okay, now sound wave can travel through a vacuum? No. Vacuum? No. Water? Yeah, it can travel. But here in option D, we have a transverse. Now, sound wave is not a transverse wave, it's a longitudinal wave. So C is the correct option. Let's go to the 15th. A quiet sound. Quiet sound means low amplitude. And remember, amplitude is the maximum displacement for the resting position. Now this, the maximum displacement of a molecule, let's call this A. This is the amplitude of the wave. It can be like this as well. It can be like this as well. Right, the loudness of the sound is increased. Now remember, loudness of a sound is directly proportional to amplitude. So that means if you're increasing the loudness, the amplitude would increase as well. Now it is asking the same thing. Which property of the sound wave is increased? Amplitude, of course. Question number 14. A man is holding a... Okay, now here we have a man who is holding a pistol. And here we have a spectator who would see this flash of light. You know, when we shot a gun, then there is a light spark, you can say, or a smoke. So there is a distance of 640 meters between them. That spectator would hear the sound after 2 seconds. We have to find the speed of sound. So we can plug in that formula, V equals to D over T. Distance is 640, time is 2 seconds. So this will be like 320 meters per second. Option B is correct. Never forget the units, okay? It's highly important in Cambridge examinations. Right, question number 15. The frequency of a musical note, again a regular vibration, is increased. Now frequency, remember this, frequency is directly proportional to pitch. So pitch of the sound. Now a student hearing the sound detects increase in which property? Pitch would be increased because both are directly related to each other. Right, in question number 16, we have a bell jar. In bell jar, initially there are so many particles. When the bell is rung, we can hear the sound. But then there is an air pump attached to it, and that air pump would suck all the air particles and throw them out of the jar gradually. So the bell would be like still ringing, but we won't be able to hear a sound. Well, that is because there is no medium anymore. No medium, because all the particles are gone from this jar. The sound waves from the bell become transverse, incorrect. Frequency of the vibration, no. Amplitude, incorrect. So that leaves us with the final option, which is D. The sound waves need a medium to travel through. Of course, there would be no medium, there would be no sound. Okay, now what about 17? What can be heard by a human ear? A whistle? Can we hear a whistle? But whose frequency is 50 kilohertz? No, that probably dogs can hear this whistle, or cockroaches, but humans cannot. A bat emitting a wave of frequency 30 kilohertz? No, we cannot hear this. It's beyond human frequency range. An insect emitting a wave of frequency 300 hertz? Yes, that is correct. Now, you know, the beetles, etc., they produce a sound in the night, which is around 300 hertz always. But the option D, a vibrating spring emitting a wave of frequency 5 hertz, no, we cannot hear it. So option C is correct. Now let's talk about the question number 18. Which row states whether light waves and whether sound waves can travel in a vacuum? Now light can travel in a vacuum, but sound cannot travel in a vacuum. So here we have the option number B, which is correct. Sound waves do not travel in a vacuum, and light waves don't really need a vacuum to propagate. Right, question number 19. Sounds are produced by a vibrating object. Yes, that is true. A certain object vibrates, but a person hereby cannot hear any sound. Well, if a person cannot hear any sound, there would be like this frequency alteration. Maybe the sound that is produced is way higher than this frequency range, because it's not really a matter of amplitude or the loudness or the speed, etc. Sound waves cannot be transverse. So yes, of course, option B is going to be the correct one. The frequency of the vibration is too high. That is the reason human cannot hear that sound, although with having a lot of like normal hearing. Okay, question number 20. Two sounds X and Y are produced by loudspeakers. The amplitude and frequency of each sound. Okay, amplitude and frequencies are given. We have two waves, X and Y. X, look at the X, the amplitude of X, it's 1.3. Amplitude of Y is 2. That would mean the Y is louder than X. But if we talk about the frequency, X has a higher pitch than Y. Okay, X has a higher pitch. You can see the frequency. Frequency is, by the way, number of vibrations per second. So there are more X produced here rather than Y. So how does Y compare with sound X? Okay, Y is louder and has a higher pitch. Well, that is wrong. It has a higher pitch, but it is not louder. Y is louder. Oops, sorry. I just did it wrong. Y is louder, of course, but it has a higher pitch. No, it has a lower pitch than X. Y is louder, has a lower pitch. Yes, option B is correct. Okay, now let's see this. A pulse of, now this is the same question. Speed of the sound is given in water. Time is given. So now you would have to like, what do you need to do? I mean, you would need this thing. Twice the distance divided by time, which is 1.2 seconds. So now you would have to like multiply this 1500 multiplied by 1.2 divided by 2, and that would give you the depth. Now how do I know that the depth was actually questioned? Well, I can see the unit, which is in meters, so I obviously know that they are talking about the depth of the sea. Okay, so I'm not going to calculate. You can calculate it with your calculator. I don't have it right now, so of course it's fairly easy. Just remember one thing: in the case of echo or reflection of sound, always use this formula, always, without any hesitation. But in the case of a normal sound or normal wave, just use this formula if distance and time is given. But if frequency and wavelength are given, then use this formula to find the speed. Right, question number 22. Approximate audible sound frequency. Okay, that's very simple. 20 hertz to 20,000 hertz. Option B is correct. Right, question number 23. A boy blows a whistle that has a frequency of 10,000 hertz. The boy's friend cannot hear the sound from the whistle. The friend has normal hearing. Okay, so there is no air damage. Everything is normal, and 10,000 hertz, that sound does come under this frequency range, so his friend should be able to hear this. Let's see what seems to be the problem. The frequency is too low? No. The frequency is too high? No. The amplitude is too small? Amplitude is really small, that's why he cannot hear it. Of course, if the amplitude was large, he would be like able to hear it, but the amplitude is too small, that's why he's not able to hear it. So it's not about frequency, it's always about loudness when it comes to like passing waves from your ear. Intensity, by the way. Okay, now here's the same thing again. I'm just gonna go with the C here because we have already done this question. Loudspeaker is gonna produce sound waves like this, and that flame would be moving back and forth because particles of the wave are moving back and forth, longitudinal nature. Here we have some couple of graphs, like 4 graphs from CRO, and all graphs have the same scale. Now they are asking which sound has the highest pitch. So pitch, like I told you, it is basically another fancy name for frequency, and frequency is number of sounds, number of vibrations. I'm just gonna write vibrations per second. Okay, so here we can see that in option A there are 1, 2, 3, 4, 5, 6, 7, 8, 9, I mean so many waves. It doesn't really have a higher frequency. D doesn't have a higher frequency. B has a higher amplitude but lower frequency. So of course it's going to be A. So A is the correct one. Right, question number 16. A fire alarm is not loud enough and pitch is too low. An engineer adjusts the alarm so that it produces a louder note or higher pitch. Okay, so initially it has low amplitude and low frequency or pitch. Now what effect does this have on the amplitude and the frequency of the sound of the alarm produced? Well, both will be larger, of course. Of course, if we are increasing the amplitude, then it will be loud, and if we are increasing the pitch, only then the pitch will be higher. So option A is correct here. Okay, in an experiment to measure the speed of sound, a student uses a stopwatch to find the time taken for a sound wave to travel from X to Y. She does this 6 times. Okay, here's the distance X to Y. Which value for the time should be used to calculate the speed of sound? Now that is a bit technical MCQs, a bit technical, because all the time there are different values of time given here, and you should decide yourself how to do this MCQs. So of course the very easy method is going to be like sound will not take that much of a time. So of course we should use like first and sixth value should be like which value for the time should be used to calculate the speed of sound. Of course what we should use is like 0.4 fourth value, because sound will not take that much of a time for reaching from X to Y. Okay, that was a logical question. Right, let's see the question number 18. A fire alarm. We have already done this. A couple of questions can be repeated, okay? So it's gonna be like, just take it lightly. 3 vibrating objects, P, Q, and R, produce a wave in the air with different frequencies. Okay, P is producing 20 Hertz, 25, Q 1000, R 15,000. Now which of these waves can be heard by human ear? Well, 15,000, yeah, we can hear it. So all of them can be heard, P, Q, and R. If you remember, 20 to 20 kilohertz, both have the same units. So yeah, all of them lie in the same frequency range. Okay, let's go to the question number 30. The diagram represents 2 sound waves. The scales in the 2 diagrams are the same. Okay, here we have 1 wave, here we have 2 waves. So that is 1 wave. Remember, it's complete 360 degrees. Here's 0, here's 90. That is 180. That is 270. And that is 360. So sound wave is basically a sine wave. Well, this one. It can be cos wave as well, but right now we have a sine wave. And here we have 2 rotations, or you can say 2 into 2 pi, which is like 4 pi. We can see 360 times, twice the 360 times. Okay, which statement describe the waves? The waves have different loudness and different pitch. Well, loudness is same in both scenarios because both have same amplitude. Since both have same amplitude, so their loudness is same, but their pitch is different. You can see, pitch is related to the frequency. For this, frequency is higher. For this, frequency is lower. So amplitude or the loudness is same. The waves have same loudness and the same pitch. Incorrect. The waves have same loudness but different pitch. That one is correct. D is correct. Right, let's go to the question number 31. A student claps once when standing 100 meters away from a large wall. The speed of sound is 330 meters per second. We have to find time. So the speed of sound at 100 meters away. So, in order to hear your voice from clapping, you should be using this formula. How long after clapping does the student hear an echo? We have to find the echo. So we are going to find this For example, we do know this formula in case of echo, this one. So we need to find time, so time will be here. That's it. 2 will be multiplied with the distance, 100, divided by 330. This will give you 200 over 330. So let's plug in the values. Let me calculate. So 200 over 330 means 20 over 33, and that will give us the value of, just give me a minute, 200 over 330, 0.60 seconds, which is, I mean, if you round it off, I mean, it is basically giving us 606. So eventually this is going to give us 0.61 seconds, which is option B. It is correct. Okay, now tuning fork is marked with the number 320. Now remember, tuning forks are those instruments, I mean, if you hit them with a rubber hammer, they will produce a sound of a particular frequency. And this number here will tell you that what is going to be the frequency of that sound. I mean, after you hit it with a rubber hammer, so it will produce a sound wave which will have a frequency of 320 Hertz. So where's the, yeah, vibrates 320 times every second. Option D is correct. So you see, 320 times every second, he is talking about, the question is talking about the frequency, because frequency is number of waves divided by 1 second. So yeah, this one is correct. Right, let's go to the question number 33. Some sound. Okay, now here we have a loudspeaker that is at point P, and some sound is going from P to Q directly by covering the 10 meters of a distance, and some sound is taking a detour, like going to R first and going to Q then. So in total it is covering 16 meters of a distance, and the speed is given. Now we need to find the difference in time for a sound wave to travel from P to Q by 2 routes. So in order to solve this question, we can use this formula, this one, V equals to D1 over T1. Let's say this is the direct, I'll just call it direct path. And then we can also use V equals to D2 over T2 for reflected path. Okay. This one is reflected path, by the way. As you know, this is a wall, so sound waves, they are reflected from a path that is flat and smooth or like hard. Okay, now let's rearrange these formulas. That is going to be like T1 equals to D1 over V, and then T2 will be equals to D2 over V. Now I'll just substitute the values for both. This is 10 over 330. And then this is 16 over 330. What do we need to do? We need to find time difference. Difference in time. Okay, now in order to find the time difference, what we're going to do, we will take delta. Delta represents the time difference, and we're just going to do this, T2 minus T1, where T2 is the reflected path, time taken by the sound via finding, like, by going from P to R and then from R to Q. And T1 is the direct one. Okay, let's just do this. We do know it's very simple mathematics then. 10 over 330. And then we can just have a simple LCM, common math, 16 minus 10. That is going to give us 6 over 330. That is the time difference. So that means option A is correct. Okay, now this one we have already covered. This question number 34, we can see the wave has the same loudness but the different pitch. Option D is correct. I've already explained to you that their amplitude is same. Their amplitude is same because both of them have the same scale, but the pitch is different, or the frequency is different, because this one, if I call this B, it has more waves per second. Okay, when the volcano Karakota erupted in 1883, it was heard 500 kilometers away. So that is the distance. Which statement about the sound of the volcano is not correct? Okay, 5,000 kilometers away. That's a huge distance. If such a loud voice would be made today, an astronaut orbiting in space at the vacuum, of course it's not possible because the astronaut is in space or in the vacuum, and sound waves cannot travel in a vacuum. People further from the volcano heard the sound later than the people nearer to the volcano. Oh, that is correct. The amplitude of the sound wave would have been smaller further from the volcano. That is correct. The sound wave was very loud because a lot of energy was transferred by the vibration of the air. Now, this one is, since we are talking about the distance, so we would be involving the time taken to hear that sound. So option B is correct. Option B, because we are talking about the distance. So the far away you are from a sound source, the late you are going to hear the sound wave. Okay, now question number 36. We have already done this, but the distance here and time is different. So we are going to do the same formula, 2d over t, plug in the values and find the value. What do we really have to find? We have to find the speed. Okay, so it's going to be 2 into 2250 divided by 3. What is the speed of sound in the sea water? So speed would be like calculated when this sound pulse is like reflected and then received at the boat. Okay, question number 37 to what is that? Estimate the. Okay, question number 37. To estimate the width of a valley, a climber starts as a stopwatch. Okay, so here's the situation. That climber wants to know the the width of this valley, means distance from here to there. So he would clap his hand, and the sound will traveling in this direction and it will come back. So it's the typical echo case. Here's the speed, the width of the valley we have to find, and the time is 1 second. Okay, so we can use this formula again, 2d over 2 over t. So it will be like Vt divided by 2 equals to d. Just plug in the values, which is like 330 into 1 divided by 2. So that would give us 1 and then 6 and 5. So 165 meters is basically the distance from this point x to this point y. 165 meters. Okay, now question number 38. A police car sounds its siren when traveling to an emergency. The siren produces two different sound waves, so P and Q, which are emitted alternately. Okay, here's the P, here's the Q, then P, then Q, PQ, etc. Okay, here in the case of P, we can see that P has a higher amplitude, but its pitch is low, means the frequency is low. Here we have 4 waves, and here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the louder sound is P, because it has a higher amplitude, and the sound with a higher pitch is Q. So P is louder, of course, sound of higher pitch P, that is incorrect. So I believe B is the option, which is going to be the correct one, because P is a loud sound, it's a very higher amplitude, and Q has a very higher pitch because its frequency is too high. Okay, question number 39. A girl stands at a distance from a large building. She claps her hands, and a short time later hears an echo. Why an echo is produced when the sound wave hit the building? Well, that is because sound waves are reflected. You do remember the formula, the phenomenon of reflection when an incoming sound hits a wall. A wall is a hard, flat surface, so it will be like reflected. So this is because of the phenomenon of reflection. Let's go to the question number 40. The diagram represent the waves produced by 4 sources of sound. The scales are the same for all the diagrams. Which sound has the highest frequency? Now, in order to know the highest frequency, we need to know how many waves are there per second. So we can see in option D is correct because there are 1, 2, 3, 4, 5, 6. So the frequency is 6 Hz. Here we have 1, 2, 3, 4, 4.5, or you can say 4. Okay, so 4 Hz. Here it is 2 Hz. And here we have like 1.5 Hz. Okay, that wave is almost half. So option D is correct. Now 3 loudspeakers vibrate. Now we have already done the similar question like this, but now we have to know if we can hear the sounds produced by these loudspeakers. 5 Hz, we cannot hear it. 25 kilohertz, we cannot hear it. 50 kilohertz, we cannot hear it. So option A is correct. We cannot hear any sound. Question number 42. A tennis player hits a ball hard, and 0.4 seconds later hears an echo, and speed is given. How far away the player from the wall? Okay, now there might be a wall like this, and that ball traveled to this wall and then reflected. Okay, so we can use this formula again. That would be v into t divided by 2, and this will give us the distance, and that distance will be the distance of a player. Let's say here a player is standing on x, and that is the distance from the wall. Okay, just plug in the values, 330 into 0.4 divided by 2, and the value will be given. Let me write the values here, or I can solve it for you. 330 into 0.40 divided by 2. Let me use my calculator. It is 330 multiplied by 0.40 divided by 2. So it is 66 meters. It is 66 meters. So the distance between the player and the wall is 66 meters. Okay, sound travels by wave motion. Which property of wave causes echo? It is reflection. Of course, that the diagram is same. Here we have a point O, let's say any point O. This is incident wave, this is reflected wave. Reflected, not refracted. A student listens to a machine that makes sound of different frequencies. He can only hear one sound. 2 Hz, not audible, inaudible. 10 Hz, inaudible. 30 kilohertz, inaudible. But 2 kilohertz, that what he can hear. A student wishes to measure the speed of sound in air. She plans to measure the time between making a sound and hearing an echo from a cliff. Okay, now this is a formula given for the distance over time, which is the speed of sound. But she can only listen to the sound if sound wave goes to this cliff and then reflected back. Means sound wave would have to cover twice the distance. So in order to find the distance, okay, so the sound would cover twice the distance, so she would have to multiply this with 2. So she would have to multiply it with 2. So continuous sound, in order to hear the continuous sound, which is like the echo, she would have to use this formula. She would have to multiply 2 with the distance, and then she would divide by time, but mainly this formula. Okay, let's see this. The diagram shows the wave shapes of 2 different sounds. The scale are same in each diagram. So here we can see again the amplitude is same for both because of having the same scale, but the frequency is different, or you can say pitch is different. So what can we really say about these 2 waves? Sound 2 is louder than sound 1. Incorrect. Sound 2 is quieter than sound 1. Incorrect. Sound 2 has a higher pitch than sound 1. Incorrect. Sound 2 has lower pitch than sound 1. That is correct. So option D is correct. Right, a sound wave travels through air as a series of compression and rarefactions. Here are the compressions where air molecules are close, and these are the rarefactions where air molecules are away. So that is rarefaction, and these are compressions. So which row correctly compares the air pressure in a compression and air pressure in a rarefaction? So here we can see that air particles are having a lot of pressure, so that is why they are very close together. So air pressure in compression is higher, but air pressure in rarefaction is lower. So option B is correct. Let's go to the question number 48. A sound wave has a certain amplitude and certain frequency. A second wave is quieter and lower in pitch. I believe we have done this one already. So the second wave has a low amplitude, smaller amplitude, and smaller frequency. Alright, in question number 49, the sound from the loudspeaker must pass through two materials to reach a microphone. So here's a material 1 and material 2. So which combination of the material gives the shortest time for sound to reach towards the microphone? Right, now speed of sound in solids, I can write it here Vs, speed of sound in solids, is greater than speed of sound in liquids, and that is greater than speed of sound in air. So in order to get like the shortest time or like transferred energy from this to this point very quickly, there has to be those materials which are solid, mostly metals. So C is the correct one, copper and aluminum. So copper and aluminum. Right, question number 50. Which range of the frequency includes only sounds that can be heard by... Well, we have done this already. This one is correct. 30 Hz to 3000 Hz. And this one is like D. We have already done it. The speed of sound in air is 340. Which row gives the typical value of the speed of sound in liquid and solids? So speed of sound in liquids is basically 1500, but in solid it's 5000. And we have done this one already, that is 1500. I mean, you can just find it earlier in the video. So that was the end of the video number 1. I'm sorry if there were a lot of disturbances in the background, but still I'm in the progress, so it would take some time, of course, but I need to remind you that if you really want to study effectively, then you should like watch my videos more regularly. I would be like uploading more and more videos on P4 soon, and then on P2, so that you can have a distinctive results in your final examination. Now with that being said, goodbye and thank you very much.